what if you could change the whole outcome of a reaction just by swapping out one atom for another?
Oh, that's interesting.
Like they're almost identical, but one's just a bit heavier. Be like, you're watching a basketball game and they sub in one player for another.
Yeah.
Looks exactly the same, plays the same, but now the team scores differently every time. In the quantum world, something like that can actually happen.
Yeah, so that actually gets to the heart of what we call the kinetic isotope effect.
Okay.
And it sounds very complex, but it really all boils down to this. Even the tiniest difference in the mass of an atom can have a surprisingly big impact on how chemical reactions actually happen.
So we're talking about isotopes, right?
Exactly.
Isotopes are,
Yeah.
I remember from chemistry class, those are atoms of the same element, but they have different numbers of neutrons.
Precisely.
So like hydrogen, for example.
Yeah, so hydrogen, the most common form is just one proton.
Right.
And no neutrons. Okay.
But then you have deuterium.
Okay.
Which is an isotope of hydrogen.
Right.
One proton, but it also has one neutron.
So it's heavier?
It's heavier. They behave almost identically chemically.
But that one neutron makes a difference.
It does, yeah.
How?
So you have to think about it in terms of energy.
Okay.
When atoms react, they need a certain amount of energy just to overcome what we call an energy barrier.
Right.
And this barrier, you can think of it like a hill they have to climb.
Okay.
And heavier isotopes, because they have more mass, they move more slowly.
So they've got less energy.
They have less kinetic energy.
Okay.
So they have a much harder time getting over that barrier.
So the reactions involving these heavier isotopes are slower.
Yeah, they're often much slower than reactions that involve the lighter isotopes.
So they're kind of like the slowpokes in a race, right?
Yeah, that's a good way to put it.
They're still trying to get to the finish line. They're just not quite as quick.
And that's what we call the kinetic isotope effect.
Precisely, yeah.
That difference in speed.
Exactly.
It's pretty mind-blowing.
It is.
That something as tiny as one neutron can make such a difference.
It really is.
But it gets even weirder, right?
It does.
When you start talking about quantum mechanics.
Yeah.
Sometimes these atoms don't even have to climb over that energy barrier.
Right.
They can tunnel right through it.
Yeah.
Like it's a ghost going through a wall.
Yeah, it's kind of like that, yeah.
So they don't even need to have enough energy.
Well, it's a quantum phenomenon.
Okay.
Where particles can pass through regions that would be classically forbidden.
Okay.
But the likelihood of that happening, of that tunneling, is extremely sensitive to mass.
Okay.
So lighter particles, like our regular hydrogen, much better tunnelers than their heavier counterparts.
Okay.
Like deuterium.
Like they've got a secret shortcut.
It's like they have a secret shortcut.
While the heavier ones have to go the long way.
Exactly. The long, energy-intensive route.
So this tunneling is also influenced by the kinetic isotope effect.
Precisely.
It all comes back to that.
Yeah, it really does.
You get a tiny little difference like a neutron.
Right, even that tiny difference.
Does affect how quickly they can tunnel.
Exactly, and that's another way the kinetic isotope effect can influence the outcome of a reaction.
Wow, so a tiny change at the atomic level can have a ripple effect that changes the whole course of a reaction.
It really is fascinating, yeah.
Incredible how the quantum world influences things on a larger scale.
Absolutely, and this isn't just some theoretical curiosity.
Yeah.
The kinetic isotope effect has a huge impact on how we understand a wide range of phenomena.
So we're not just talking about something in the lab.
No, not at all.
This has real-world implications.
Oh, absolutely.
Like what?
Well, for example, it's incredibly useful for scientists who are trying to understand the intricate details of how chemical reactions work.
Okay.
Particularly in complex systems like living organisms.
Okay, so how does the kinetic isotope effect help us understand these reactions in the real world?
So one of the key applications is in the study of enzymes. So one of the key applications is in the study of enzymes.
Enzymes.
Yeah.
Those are...
These are like...
I remember learning about these...
biological catalysts that speed up.
They make all sorts of important processes happen in our bodies, right?
Exactly.
Like tiny machines.
Yeah, and because they're so crucial for life, scientists are always trying to figure out how they actually work.
Right.
And the kinetic isotope effect turns out to be a really valuable tool for that.
Okay, but how? I don't really get the connection.
So imagine you have this enzyme that helps break down a particular molecule.
Okay.
And let's say that molecule contains a carbon-hydrogen bond.
Okay.
That has to be broken.
That's part of the reaction.
That's part of the reaction, right?
Okay.
So the enzyme comes along, helps to break that bond.
Right.
Now, let's say we swap out that hydrogen atom for a deuterium atom.
Okay, so we're using that heavier hydrogen
Right, the heavier hydrogen, exactly.
So now it's a carbon-deuterium bond.
Right, instead of a carbon-hydrogen bond.
Okay, so then what happens?
Well, if breaking that bond, that carbon-hydrogen bond, is a crucial step in the reaction, then we would expect to see a pretty big difference in the reaction rate.
When we use a deuterium instead of a hydrogen.
Exactly. The heavier deuterium should slow down the reaction.
Okay, so we can see how the reaction changes when we swap in the heavier isotope.
Yeah.
And that gives us clues about how the reaction works.
Precisely.
We can see which steps are really affected by that heavier atom.
Exactly. The kinetic isotope effect is like a magnifying glass.
Okay.
It lets us zoom in.
On that one specific part.
Yeah, on the specific steps of how the enzyme is actually working.
So it's not just about seeing, oh, the reaction slowed down.
Right.
We're using that information to try to really understand how the enzyme works.
Yeah, like what's the mechanism?
Okay.
And this is so useful because it can help us design drugs that target specific enzymes. New biotechnological processes or even engineer enzymes with enhanced capabilities.
It's incredible to think that something as simple as just how heavy an atom is
I know, it is pretty amazing.
can affect things like medicine and biotechnology.
Absolutely. And there are other areas too where the kinetic isotope effect comes into play.
Oh, really? Like what?
Well, it's also used a lot in environmental science,
Okay.
particularly when studying atmospheric chemistry.
Atmospheric chemistry.
Yeah, so you know the atmosphere. It's this complex mix of gases. There's all sorts of reactions happening up there all the time.
Yeah.
And these reactions play a really crucial role in determining things like
Okay.
air quality,
Yeah.
climate, and even the ozone layer.
The ozone layer, the one
Yeah.
that protects us from the harmful UV rays from the sun.
Exactly.
Okay.
And the kinetic isotope effect can actually help us understand these processes
Okay.
that are involved in ozone formation and also ozone depletion. So, for example, by analyzing the isotopic ratios of oxygen in ozone molecules, we can figure out where that ozone came from and how it's being destroyed.
So it's like a fingerprint.
Yeah, it's like a fingerprint.
That lets us track where the ozone's been.
Yeah, and we can understand, how human activities are impacting that really vital layer of the atmosphere.
Right.
And maybe even come up with ways to protect it.
It's fascinating that the kinetic isotope effect is this tool that can be applied
I know, it is pretty cool.
in so many different areas.
Yeah.
We go from physics and chemistry
Yeah.
to biology and environmental science,
It all connects, even the atmosphere.
and even beyond our own planet.
Oh, right. We were talking about how the kinetic isotope effect might have been involved in how life first formed.
Right, right.
That was really mind-blowing.
It is kind of mind-blowing.
That something happening at the level of atoms could affect the origin of life itself.
Yeah, potentially even on other planets. It makes you think that even the smallest things can have huge implications.
It really does.
It's a whole hidden world of complexity that's happening at levels we can't even see.
That's one of the amazing things about the kinetic isotope effect. It gives us a glimpse into that hidden world.
Right.
It lets us unravel some of the mysteries that govern how matter behaves.
Right. At the smallest level?
At the most fundamental level, exactly.
This has been so insightful.
Oh, glad you enjoyed it.
It seems so abstract at first.
I know. It can seem that way.
It turns out it's so important to so many different areas of science.
Yeah, it really is.
But I have to ask, are there any areas where our understanding is still a bit fuzzy?
Oh, that's a great question. And the answer is definitely yes. There's always more to learn and explore.
Okay.
We've made incredible progress in understanding the kinetic isotope effect.
Yeah.
But there are definitely still some frontiers out there where we're pushing the boundaries of what we know.
Like, what are the mysteries that are still out there? What are scientists still scratching their heads about?
Well, one of the big challenges, I think, is understanding the kinetic isotope effect in really complex reaction networks.
Okay.
So, in the lab, we often study reactions in isolation.
Right.
But out there in the real world, things are a lot messier.
Okay.
You might have multiple reactions all happening at the same time, all influencing each other.
Yeah.
Different isotopes playing different roles.
So it's like trying to figure out what one dancer is doing
Yeah.
in a huge choreographed performance where everyone's moving together.
Exactly. It's like a giant dance.
Okay.
And in these complex systems, it can be incredibly difficult to isolate, what's the contribution of the kinetic isotope effect?
Right. Just that one tiny little change.
It requires really sophisticated experimental techniques and theoretical models
Okay.
to tease apart all the different factors.
And really see what's going on.
Exactly.
So it's like a giant puzzle.
It is. It is.
Where the pieces are always moving.
Yeah, that's a great way to put it.
What other frontiers are there?
Well, another really exciting area is developing new analytical techniques to measure isotopic ratios, but even more precisely, even more sensitively.
Okay.
Because the more accurately we can measure these ratios, the more subtle effects we can detect.
It's like getting a better microscope.
Exactly.
To see these tiny changes in even finer detail.
Precisely, yeah. And advances in things like mass spectrometry are pushing the boundaries of what we can actually measure.
Yeah.
We're able to see tiny variations that we couldn't see before.
So as our ability to measure gets better, our understanding will get better too.
Absolutely. It's like an ongoing journey of discovery, you know? The more we learn about the kinetic isotope effect, the more we realize how much we don't know.
Right.
But that's what's so exciting about science, you know?
Yeah.
It's a never-ending quest.
To figure out the mysteries of the universe.
Exactly.
It's been incredible exploring this concept with you.
It's been a pleasure.
We started with something so simple.
Yeah.
The mass difference between two atoms.
Yeah.
And now we're talking about medicine, environmental science, even astrobiology.
It really highlights how interconnected science is.
Yeah.
And who knows what other secrets the kinetic isotope effect holds.
Right.
What other applications or implications we might find in the future.
It's amazing to think about all the possibilities.
It is.
Maybe one day we'll use this to understand even more about the origins of life.
Yeah, who knows?
Develop new technologies or solve some of the big environmental problems that we're facing.
It's a good reminder that sometimes the most amazing discoveries come from exploring even the tiniest details.
Well said. Thank you so much for joining us on this journey into the world of the kinetic isotope effect.
Oh, you're very welcome.
It's been a real eye-opener for me, and I hope our listeners enjoyed it as much as I have.
It's been my pleasure to share my passion for this topic, and to all the listeners out there, remember the next big scientific breakthrough. It might be hiding in plain sight, just waiting for someone with a curious mind to uncover it.